Hello everyone. In this video we are going to talk about the three-phase circuits delta Y connection. So here, as you can see in this figure, we have delta our load is in delta form, so which is like this, and we have a current going IA, and we also, since in the previous video we talked about the three-phase circuits in Y to Y connections, and also we're considering in a balanced condition, so their impedances should be equal. So these impedances are equal to each other. Now, if you haven't watched the previous video, which is balanced three-phase Y to Y connection, I highly suggest you to watch that video if you're not familiar at all, and then come to this video. Okay, now, as you can see here, in the delta connection, we have phase currents. What are the phase currents? Well, the phase currents are IAB, IBC, and ICA. These are for each phase, they have these currents. And what about the phase voltages? Well, VAB, VBC, and also VCA. Under the balanced conditions, the phase currents are equal in magnitude and have 120 phase difference. So, for example, if our IAB has a magnitude of IP, it has some magnitude, and also it has some alpha phase, then IBC will also have the same magnitude, but 120 degrees in the clockwise direction difference. Also, ICA will have the same condition, and another 120 degrees, so it will be minus 240 degrees, or we can write it as plus 120 degrees, which they are the same. Okay, so what do we notice? Well, by KCL, we can see that IA is here, and IAB and ICA. What can we say KCL in this node A? Well, by KCL, we can understand that IA will be equal to IAB minus ICA. Okay. Now, let's draw a phasor diagram for this condition. Now I have draw the phasor diagram for both cases when we had Y to Y connection and also delta Y connection. So we can see that this is for delta Y connection. As you can see, they are very similar. These two diagrams, they're very similar. It is like they're dual of each other. Okay, so What did we say? We said IA equal to IAB minus ICA. So if we have IAB, then minus ICA will be this one, this vector. And if we add them, we will get IA, which is this one, right? So, and due to these 30 degrees, as it is clear, then the magnitude of IA will be radical 3 times Vm. If IAB, for example, has a, this is IM. Okay, not Vm. Okay. Now, if they have this magnitude, then the IA will have radical 3 of that magnitude. So this is the phasor diagram, and you can clearly see their differences. And once you found one of these, then the other ones are easily can be found by 120 degrees rotation in the clockwise direction, and everything will be complete. So these phasor diagrams are extremely important in analyzing the problems. So what we notice? Well, in Y connection, the load line magnitude will be equal to radical 3 of the phase potential, and we saw that the load line will be equal to the phase line. Okay, but in the delta connection, the load current will be equal to the line current, the line current will be equal to a radical 3 of IP. And the potential of the line magnitude will be equal to the magnitude of the each phase in the load side. So these are very important, and we need to remember these parts. Okay. Now, to make, if you remember, to make use of the per phase circuit, we can apply delta Y transformation to the load. In the previous video, we talked about the per phase analysis. So in order to use that one, we can transform the delta load to the form of the Y load. So we need to know this tip and trick, that if we have a delta load, something like this, this is node A, this is node B, and this is node C. And if they have Z delta impedance, then their equivalent will be in the Y form, as something like this. Then this is equivalent of node A, B, and C. Then the impedance, we say ZY for each of these. And ZY should be equal to 1/3 of Z delta. So this is very important whenever you want to convert the load from the delta form to the Y form. You just need to get 1/3 of each Z delta to get the ZYs on the Y form of the load. So then the equivalent of the per phase, which we learned in the previous video, is this figure. Line impedance, and this is ZY, which will be equal to 1/3 of Z delta. Okay, now let's go and solve a question and example to see how we can deal with these problems. Okay, in this example, we are given a delta connected load with per phase impedance 75 plus J 225 ohms, which is supplied with the power from a Y connected generator whose phase voltage is 110 VRMS. The transmission line impedance is 10 plus J5 ohms, and it says take VAN on the generator side as reference. Find phase currents of the load, line-to-line voltages on the load side, and also real power consumed by the load. So this is a typical example. First of all, this per phase circuit is very important. So since this is given as a delta form, we need to convert it to the Y form. In order to do that, we need to write the per phase circuit. Which is something like this. And it is giving that the phase voltage is 110 VRMS. So since it is given as VRMS, the real magnitude of the voltage should be VRMS times radical 2. So it will be 110 square root of 2. Since it says that VAN on the generator side, take it as a reference, so its phase difference should be 0 degrees. Okay, you can say it like this. Now, the line voltage, the line impedance is given as 10 plus J5 ohms, and the Z delta is given as 75 plus J 25 ohms. But please remember that if you want to use the per phase circuit, you need to convert it to the ZY. So Z delta over 3 will be ZY. So ZY, the equivalent one, will be, if you divide it by 3, it will be 25 plus J 75 ohms. Now, it says find the phase currents. It means IAB, IBC, and ICA. So first of all, we can find IA, this one, the little l, A. This is equal to the voltage over the impedance, right? From the Ohm's law. So it will be 110 radical 2 with phase 0 over 35 plus J80. So the denominator is given as in the rectangular form, so we need to convert it to the polar form like the numerator. And with that calculations, we will get 1.78 with the phase difference of minus 66 degrees amps. Okay. Now, what is IAB? Well, we know how to get from this expression to IAB, and once we found IAB, the other ones are much more easier to get VBC, IBC, and ICA. Just we will go minus 120 degrees in the clockwise direction. Okay, this is easy. So here we have this and we want to find this one. How can we find it? Well, the phase will be at 30 degrees. We will add 30 degrees phase, and also the magnitude will be shrinked. Will be shrinked by 1 over radical 3, right? So we need to IAB will be IA times 1 over radical 3 with the phase of 30 degrees. And this will give us 1.3 minus 36 degrees amps. So once we have this, then IBC will be just the same magnitude, but we need to subtract it with minus 120, so it will be minus 156, and ICA will be 84 degrees. You can add 120 to this one, okay, to get 84 degrees. Now we found the phase currents from part A. So part A is finished. What about the line-to-line voltages on the load side? Well, line-to-line voltages are VAB, which are equal to Z delta times IAB, right? So consider this one in the schematic. This is plus minus due to the passive sign convention. The current is going always from the positive to the negative. And it also has the impedance of Z delta. So VAB, which is the line-to-line voltage on the load side, is equal to this expression because of the Ohm's law. So from here, we can say what is Z delta. it is 75, it is given here. 75 plus J 225 times 1.03, which we found this expression with the phase difference of minus 36 degrees. And this is also given as a rectangular form. You need to convert it to the polar form. Then we can multiply the magnitudes of them and add the phases. And then we will get 244 with the phase difference of 35 degrees volts. So if you found one of them, then the rest is easy. Then VBC and VCA will be found. Just subtract with 120. The magnitudes will be the same. So this will be this. Okay. So again, instead of subtracting minus 120, I just added 120 from there. Okay. Now what about the part C? We did part B, but what about the part C, the real power consumed by the load? Well, what was the expression for the power? The real power or average power of the load for one of the loads will be, for one of the Z deltas per phase, I'm saying about per phase, will be IAB RMS value squared times the real part of the Z delta. Okay. Now this is equal to IA RMS value squared times the real value of the ZY, because we know this is a radical 3 times bigger than this one. Okay. And this is also this one is 3 times ZY. So we will get the same results. So it won't change anything. So we can write the expression like this. So we are increasing by radical 3 over 2. And here we are decreasing by 3 factor. So overall, the expression won't change. So this is valid expression. So from here, we will get radical 2 square times 75. Then we will get 39.8 watts. So the unit is watts for the real power and the average power. And then the overall power, which is the total power, real power, will be 3 of PA, which will be 119 watts. This was a good example of showing how to convert the delta load to the Y form and use the per phase analysis to get phase currents, line-to-line voltages on the load side, and also the real power as well. I hope this video was useful, and thanks for watching.